Hello, and welcome to this special episode of the Little Red Podcast. I'm here with guests Dr. Sarah Percy and Dr. Sean Turnell. As you probably know, last week the Nobel Prize for Physics was awarded to Pierre Augustin, Ferenc Krosh, and Anne O'Willier for their experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. Today, however, we will explore a different use of attosecond pulses of light, namely in solar cells. So let's get started. Solar cells convert sunlight into electricity and are one of the key technologies to harness renewable energy sources. In the past decades, their efficiency has steadily increased from around 10% in the early days to almost 20% today for lab-scale cells. While this might seem respectable, it's still far off from the theoretical maximum of close to 30% and definitely too low to meet the enormous demand that we will face in the future. One major challenge that hampers further improvement of solar cells is our limited understanding of the physical processes that take place in them. Just think about it. When sunlight hits a solar cell, electrons are set in motion within fractions of a second. They then need to be collected before they recombine with the holes that they left behind. The relevant timescales are so short that studying these processes requires light pulses that are shorter than the timescales themselves. The human eye sees the world in shades of black and white, because it takes time for the photoreceptors of the eye to adapt to changes of illumination. This means that for the eye, everything happens in shades of gray, and colors only appear when the eye adapts to new levels of illumination. However, this is not the case for cameras, and many photos taken with them look quite different under different levels of illumination. They show different shades of colors depending on the lighting conditions. If you want to change the color of an object in a photograph, you don't need to change its position or add something else to the scene. You simply change the illumination and you can make it appear red, blue, or green. Even worse, changing the amount of illumination can significantly affect the appearance of objects in a photograph. Sometimes it can even completely change their appearance, as you can see here. Now imagine a situation where the brightness and color of the light source keep changing continuously. The problem becomes even worse. All these examples demonstrate that taking photographs is challenging in varying illumination. Most sensors are calibrated under controlled conditions where the illumination is known and reliable. For example, camera sensors are calibrated in the laboratory, where the intensity and color of the illumination can be carefully controlled. However, if the illumination keeps changing, as is the case outdoors, it is difficult to know the exact color and intensity of the illumination. Since these conventional cameras are calibrated under different conditions, they return images that need to be corrected for the changing illumination. However, in the end, the resulting image may still look distorted, and this distortion depends strongly on the scene itself. Therefore, you need algorithms that can deal with these variations, especially considering that these algorithms must run in real time on resource-constrained devices. In a recent publication, a team of researchers led by Professor Peter V. Hai and Dr. Shervin Minaj from Nanyang Technological University, Singapore, addressed just that problem. They presented a machine learning algorithm that learns the behavior of the sensor under varying illumination and automatically corrects the image. More specifically, they learned the nonlinear mapping between the raw signal of the sensor and the color of the illumination. This nonlinearity arises since the signal of the sensor is affected by multiple physical processes and may not be directly proportional to the color of the illumination. To achieve this, the authors developed a physics-based model that describes the sensor response to the illumination. The model can simulate the change of the sensor signals under different illumination, and this allows the algorithm to learn the nonlinear behavior of the sensor. Once trained, the algorithm can automatically correct the images by removing the effect of varying illumination. To test their algorithm, the authors used data from a custom-made RGB camera with a CMOS sensor. The raw data of the sensor was recorded together with a reference signal that describes the true color of the illumination. This allowed them to train and test their algorithm, and the results were impressive. On average, the proposed method outperformed previous techniques by 20%, especially when the illumination changed abruptly. The proposed method showed excellent performance even if the color of the illumination changed slowly. This robustness is extremely important for outdoor applications where the illumination can change quickly or slowly. However, one crucial aspect of the paper is that the authors provided evidence that their method can be generalized to other sensors, meaning that it's not limited to the sensor used in their study. They demonstrated this by showing that their method could be used to correct images from sensors with different spectral responses. This opens the door to a wide range of possible applications. So why is this work important? Well, I'll tell you. There are more than 10 billion cameras in the world today, but few of them deliver the raw signal that can be used to implement such an algorithm. However, more and more devices come with dedicated hardware to extract the raw signal of the sensor. Moreover, new sensors are increasingly being developed to be sensitive to wavelengths beyond the visible spectrum, such as infrared or ultraviolet cameras. These cameras could benefit immensely from this algorithm, as they often suffer from severe illumination problems. Another important point is that the algorithm can be implemented on microcontrollers, opening doors to resource-constrained scenarios. This has direct implications for tiny embedded systems like those found in smartphones, wearables, autonomous driving systems, and IoT devices. And this is great news. Imagine if your smartphone camera could correct for the varying illumination, without having to rely on cloud computing. Think about how useful that would be for social media applications. Or consider autonomous driving. Most current techniques for autonomous driving rely on multiple sensors to improve accuracy and reliability. However, sometimes these sensors disagree, which creates challenges for the overall system. If we could trust the camera even more, we would need fewer sensors, making the system cheaper and more reliable. One final comment: I feel that papers on machine learning and physics are becoming more and more intertwined. Of course, the reason is that most natural phenomena are best described by the laws of physics, and this paper is a perfect example of this. By integrating the laws of physics into their model, the authors were able to create an algorithm that works better than those that don't use this prior knowledge. This trend will likely continue in the future, leading to even more accurate and efficient algorithms. So how does this work fit into the bigger picture of solar cells? Well, let me tell you. The efficiency of solar cells depends strongly on the materials they are made of. For instance, silicon is commonly used, but other materials like perovskite are gaining popularity due to their higher efficiency. Perovskite solar cells have already reached efficiencies of over 30% in lab conditions, surpassing the theoretical limit of single-junction silicon solar cells. These new materials, however, also present challenges. they are more susceptible to environmental factors and may degrade over time. Understanding the degradation mechanisms is crucial to develop countermeasures and increase their lifespan. One approach to study these degradation processes is to expose the solar cells to various conditions and monitor their performance. But this is a slow process and may take years to observe significant degradation. Additionally, it's difficult to isolate the effects of each environmental factor, such as moisture, temperature, or UV radiation. This is where attosecond pulses of light come in. By using short and intense laser pulses, researchers can accelerate the aging process and study the degradation mechanisms in real time. Attosecond pulses allow scientists to observe the dynamics of electron-hole pairs in solar cells under various conditions. Studying these dynamics provides insights into the factors affecting the efficiency and longevity of solar cells. One particular advantage of this technique is that it can be performed in a controlled laboratory environment. This means that researchers can isolate specific environmental factors such as temperature, humidity, or UV exposure, and study their individual effects on the solar cells. By understanding how different factors contribute to the degradation, researchers can develop strategies to mitigate their negative impacts. And this brings us to a recent paper published in Nature Materials. The authors used attosecond pulses to investigate the degradation of perovskite solar cells under UV radiation. They found that UV exposure causes the formation of defects in the material, leading to reduced efficiency. Interestingly, they also observed that the presence of an electric field can hinder defect formation, suggesting a potential strategy to mitigate UV-induced degradation. Overall, this research highlights the potential of using attosecond pulses to study the degradation mechanisms of solar cells. By shedding light on these processes, researchers can pave the way for developing more durable and efficient solar cells, which is essential for the transition towards sustainable energy sources. And that concludes our special episode on attosecond pulses of light. I hope you enjoyed it. If you did, please leave us a review. And if you'd like to see more episodes like this, subscribe so you don't miss any of our new episodes. And until then, keep thinking in pictures.